This video is on section 8.4 notes, testing a claim about a standard deviation or variance, but honestly we're just doing standard deviation. So this example says U.S. Mint specifications require that quarters that are manufactured after 1964 have weights with a mean of 5.670 grams and a standard deviation of 0.062 grams. Listed below are weights in grams of a simple random sample of quarters made with a new minting process designed to reduce the standard deviation so that weights of quarters are more consistent. Use a 0.05 significance level to test the claim that these weights are from a population with a standard deviation that is less than 0.062 grams. And then it gives you the sample. So first, identify the claim to be tested and express it in symbolic form. So because we're talking about the population standard deviation, we're going to use the variable sigma this time. So we're testing that sigma is less than 0.062 grams. The opposite of this is that sigma would be greater than or equal to 0.062 grams. The null hypothesis is always whichever one of these includes the equal sign, and we're going to go for just the equal sign, not using the inequality part. So sigma is exactly 0.062 grams, and so the null hypothesis is going to be that sigma is the other one. So equal sign for this one, and then we'll use this one. Sigma is less than 0.062 as the alternative hypothesis. The significance level 0.05 is what the problem said. I went back and got the table that I used in step 5 from the very first section we went over in chapter 8. Section 8.1 has the whole table, and I went through and just chose the row that's going to be appropriate for today. And so that is for standard deviation, where we calculate the chi-square. So we're going to be using the chi-square distribution table, and we're going to be calculating this as our test statistic. Now, based on the symbol, we have for our null hypothesis and our alternative hypothesis, we have a less than symbol, which means that we're going to have a one-tailed test, and it's going to be a left tail. So we have one tail, and it's specifically the left tail. So I'm going to go through and write down what each of the variables are that we're going to need to define. So we're going to need S, the sample standard deviation, sigma, the population standard deviation. We're going to need N, and then because we're going to use the chi-square, we're going to need the degree of freedom. All right, so we are going to be calculating just the left chi-square because this is left-tailed. So if we look at this problem, we have sigma was 0.062, and we need to calculate the standard deviation because this is a problem where they gave us the sample, so I'm not going to do that yet. I am going to find the sample size and the degree of freedom though. So we have 3 times 8. There are 24 pieces of data here, so our sample size is 24 and our degree of freedom is 23. Okay, so I would go into my calculator, my TI-84, and click the stat button, and then I would edit, and in here I would put all those different pieces of data we have, and just to save time in this video, I've already done that. So this is the 24 different numbers that came from this example. So once you're done typing them in, you'll hit the stat button, calculate, go right to calculate, and we're going to calculate one variable statistics and press enter. All right, so we have the mean, we don't need that. We do need the standard deviation for this, and I'm going to write down 4 digits. So 0.0480. And so my chi-squared value is going to be the degree of freedom, n minus 1, times s squared divided by sigma squared just make sure I got those numbers right. And so the chi-square that I got is 13.7856. Okay. And I'm going to go ahead and draw my chi-square distribution table. And the chi-square distribution table looks like this. And I have a left tail, so using my table, degree of freedom is 23. I'm going to be somewhere in here. This is for the left. And I'm going to use 0.95 since my my alpha was 0.05. So I'm going from here down 23. I get 13.091. So if this value is to the left of this number, then it's in the rejection zone or the rejection region. And if it's to the right of that number, then it's not in the rejection region and we fail to reject the null hypothesis. So when I look at this, I can see that 13.7856 is just a little bit to the right. So we're going to fail to reject the null hypothesis. I still want to make my conclusion based on the p-value. I want to do it both ways so that you guys can see both ways. So this was using critical values. Now I'm going to go ahead and calculate the probability that chi-square is less than 13.7856, and I'm going to compare that with my significance level. So I'm going to grab my chart, 13.7856. I'm going to look at my degrees of freedom, and I'm going to look for 13.7856 and find it on the chart. So it's in between these two numbers. I'm going to just write 13.8. So 13.8, and I'm going to go up here, is between 0.95 and 0.90. So that would be, this is an alpha value of 0.05. This is an alpha value of 0.10. And so if this is what we have, then that means that this p-value is between 0.5 and 0.10. So this p-value is between 0.05 and 0.10. And in order for us to reject the null hypothesis, our p-value had to be less than 0.05. And we don't know what the p-value is. It could be any decimal in between these, but we do know that it's between 0.05 and 0.10. It is definitely greater than 0.05. So P is greater than 0.05. That means that P is greater than alpha. It is greater than the significance level. And so we fail to reject the null hypothesis. So there's two ways you can do it. You can compare the test statistic with the critical value that you get from the significance level that you get from the alpha. So take the alpha, use your chi-square distribution table and find the rejection region, and then see if this places your data in the rejection region or not. The other way is to find the p-value and compare the p-value to that alpha value and see if it's smaller or not. Two different ways to do it. I've been doing both because I'm helping you guys do notes and learn what you're doing. You do not have to do both when you do this on your own for homework. You can choose the method that you like and only use that method. Okay, so we have to restate this decision in simple and non-technical terms. And so we're going to look, did the original claim have the equal sign? The answer was no. Did we reject or fail to reject? We failed to reject. And so our sentence is going to be, there is not sufficient evidence to support. There is not sufficient evidence to support the claim that the population standard deviation of weights of quarters is less than 0.062 grams. All right, let's go ahead and look at the next example. This one says the pulse rates for a random sample of 40 women is found to have a standard deviation of 11.6 beats per minute. Use a 0.05 level of significance to test the claim that the standard deviation for all women's pulse rates is 10 beats per minute. So this says the standard deviation for all women is 10 beats per minute. So the population standard deviation is 10 beats per minute. Oops, BPM. The exact opposite of that would be sigma is not 10 BPM. So the null hypothesis is the one that has the equal sign. Sigma is 10 BPM. And then the the alternative hypothesis is the opposite. So this is the one that had the equal sign. So this one is the alternative hypothesis. The significance level is 0.05. And we know since we're working with the population standard deviation, we're testing that claim that we're using chi-squared. All right, so let's move to the next page. I did copy over the example wording, but I didn't copy over the formula, so I'm going to go ahead and write that. Chi-square is n minus 1 s squared over sigma squared. So we need to know the value of s and sigma and n and the degrees of freedom. So S is the sample, 11.6. What we're testing for the population is 10. The sample size is 40. The degree of freedom is 39. What we learned based on the way that this null hypothesis and alternative hypothesis are written is that we are doing a two-tailed test because this says sigma does not equal 10. So that's going to be the left side and the right side, less than 10 and greater than 10. So that will be important in a minute. That means we're going to have to find our chi-square for the left side and our chi-square for the right side. But first, we're just going to find our test statistic, which means we just need to calculate this in general before we compare it to our critical values and our rejection regions on the left and right. So we're going to have 40 minus 1 s squared over sigma squared (52.4784). Well, not approximately, it is equal. Equals 52.4784. All right, now for the alpha, we had alpha is 0.05, but we have to think about that on the left and on the right. So that's 0.025 on the left, 0.025 on the right. So we're going to use 0.025 on the right. 1 minus 0.025 is 0.975 on the left. We're looking for a degree of freedom of 39, but I don't think this chart has 39. So I'm going all the way down. We don't have 39, we have 40, so that's what we have to use. So our two critical values are 24.433 and 59.342. So that's what I'm going to be drawing in when I draw this distribution and put my left tail and the right tail with the rejection regions on each side. So 24.433, 59.342. So let me go ahead and draw this. Looks like that. (24.433, 59.342). So if our test statistic is less than 24.433 or greater than 59.342, that's when it would be in a rejection region. Ours is not. Ours is kind of in between. So this, but it's closer to the 59. So I'm going to draw this over here. Our 52.4784 is in the it's not in a rejection region at least. So acceptance region, but we're not going to reject. I'm still going to calculate the p-value so we can see how that would work on this problem. So we want to find the probability that t, and since, sorry, not t, chi-square. We want to find the probability that chi-square, and here we would kind of see, is it closer to the right tail rejection region or closer to the left tail rejection region? And this one looks like it's closer to the right tail. So I'm going to find the probability that chi-square is greater than 52.4784. And so I'm going to take my chi-square distribution table. I'm going to look at the degrees of freedom of 40 because 39 is not on the table. And I'm going to try to see what values 52.4784 is near. So 40, I'm looking for 52. Oh, it's right in here. 52.5 is right in here. 52.5, and so I'll go up. And this is between 0.10 and 0.05, but I have to divide those in half. Sorry, I misspoke. I don't have to divide those in half. It's in between 0.10 and 0.05. So you can see that it's getting smaller as we look over here. So 52.5 is in between a value of 0.10 and 0.05. So my p-value is in between 0.10 and 0.05. Okay, so I'm going to write that down. My p-value is between 0.10 and 0.05, and I'm going to write it like this so I have the smaller value on the left and the larger value on the right. Now, if this was a one-tail test, I would leave these as my p-values. But this is not a one-tail test, this is a two-tail test, so we have to double it. So I'm just going to take this, I'm going to write double because two-tail test. And we didn't have to do this when we were working in section 8.3 because section 8.3 had two rows at the very top for us, and one of the rows said one-tail test and the other said two-tail test. So for a t distribution in section 8.3, we didn't have to worry about this. But now for section 8.4, we do have to worry about this because our distribution table doesn't spell it out for us. So we're going to double this, and so this means that the p is really in between 0.20 and 0.10. Okay, the p-value is between 0.20 and 0.10, and if we look at this, our p-value is supposed to be less than 0.05 if we're going to reject the null hypothesis, and so p is definitely greater than 0.05, and so we're going to fail to reject the null hypothesis. Fail to reject the null hypothesis. So we have two reasons we know we can reject the null hypothesis. One is using critical values, the other is using p-values. And you don't have to do both, you can choose one or the other. All right, so did the original claim contain the condition of equality? Yes, it did. That's why we had a two-tail test. We failed to reject the null hypothesis, and so we're going to be writing this type of sentence. We're going to say there is not sufficient evidence to warrant rejection. Of the claim that the standard deviation for all women's pulses, or pulse rates, for all women's pulse rates is 10 beats per minute. All right, last example. 12 speeds of southbound vehicles on I-280 were recorded at 3:30 p.m. on a weekday. They were found to have a standard deviation of 4.075 miles per hour. Use a 0.05 significance level to test the claim of the highway engineer that the standard deviation of speeds on I-280 is 5 miles per hour. So the highway engineer said that the standard deviation of speeds on I-280, that like the standard deviation of all speeds on I-280 or the population on I-280 is 5 miles per hour, and they use the word is, and so that's an equal sign. So they're saying that sigma is 5 miles per hour. And so the opposite of that would be that sigma is not 5 miles per hour. So the null hypothesis is always the equal sign. Sigma is 5 miles per hour. The alternative hypothesis is the opposite, or the other one. So sigma is not 5 miles per hour. And so just like the last example, we're going to have a two-tailed test. Our significance level is 0.05. That seems to be the favorite for section 8.4 for these examples at least. Again, we have that same formula. So find the value of the test statistic. So we need to know the standard deviation for the sample and the population. We need to know the sample size and the degree of freedom. So the standard deviation for the sample was 4.075. For the population, it's supposed to be 5. The sample size was 12, and so that makes the degrees of freedom 11. So chi-square, when I calculate it, is going to be 12 minus 1 times 4.075 squared over 5 squared. $7.3065. Okay. And I'll go ahead and draw my distribution. Left tail, right tail. Okay, so my degrees of freedom is 11. Because my significance level is 0.05, I have to take that 0.05 and divide it in half to do my left tail and right tail. So 0.025 for the right. The complement of that is 0.975 for the left. And then I'm going to work my way down to that degree of freedom. And so my two critical values are 3.816 and 21.920. So 7.3065 is in between the two critical values. It is not in those rejection zones or those rejection regions. So we are about to fail to reject the null hypothesis. But we're going to go ahead and do it with the p-value, even though we just figured it out based on the critical values. So I want to find the probability that chi-square is either less than if I think 7 is closer to this side, or greater than if that 7 is closer to this side. And I think 7 is closer to 3.816. And so I'm going to say the probability that chi-square is less than 7.3065. And so I'm going to grab my distribution table and I'm going to figure out where 7.3065 falls on the table. So here's my degrees of freedom, and I need to find, so it's in between here. So 7.3 is somewhere in between here. So 0.90, 0.10, 0.90 is really a significance value of 0.10. And you can look here. So we've got significance value of 0.005, 0.010, 0.025, 0.050, 0.10. These values are getting larger. 0.995, 0.99, 0.975, 0.95, 0.9. These A values are getting larger. So what we know is if this is in between, it's showing where the A values would be larger. Maybe this is 0.10, maybe it would be 0.20, maybe it would be 0.30, maybe it would be 0.40. We don't know where it would be. We just know that the A value is greater than 0.10. And it could be over here on the left side, or it could be over here on the right side. We don't know. We just know that it's greater than 0.10. So I know that this is greater than 0.10. But again, this is a two-tail. So we're going to double it. So the p-value is greater than 0.20. That's what we know. So we were going to reject the null hypothesis if the p-value is less than the alpha value, if it's less than the significance level. The p-value is 0.20. P is not supposed to be greater than 0.05, but P is definitely greater than 0.05. 0.20 is definitely greater than 0.05. And so we are going to fail to reject the null hypothesis. All right, so to write our sentence, the original claim had equality. It had that sigma equaled 5 exactly. We failed to reject the null hypothesis, and so we're going to write our sentence using that sentence starter. So we're going to say there is not sufficient evidence to warrant rejection of the claim that the standard deviation of all speeds on I-280 is 5 miles per hour.